Streams of hot material curving in huge arched paths are dramatic evidence of the invisible magnetic field of the sun, but some fast particles escape into space. After a journey of 150 million kilometers, they encounter the Earth's magnetic field, stretching hundreds of kilometers from the surface. Most of the stream of particles is deflected around, but some enter the atmosphere and produce glowing auroral displays, known in the northern hemisphere as the northern lights. Well, if you come to a place like Iceland, particularly on a horrible day like this, and you want to navigate with a compass, you need to be rather careful. Let me explain. The cliffs you can see behind me are actually due north of me on the map. If I set my compass up on the map, you can see that north actually points out over in that direction rather than towards the cliffs. That's the angle of declination, and the reason for it is because the magnetic North Pole is not coincident with the geographic North Pole. In fact, the magnetic North Pole is situated somewhere over northern Canada. Furthermore, if I take a vertically mounted compass needle with a horizontal axis and set it up, it would point down at about 77 degrees. And if I was to walk in a line from here out towards Canada, that inclination, the angle between horizontal and that vertically mounted compass needle, would increase towards 90 degrees until it actually pointed straight down into the Earth. And that's the magnetic dip pole.
If the dip of the field varies from place to place, does it vary in any systematic way? Well, the Earth's magnetic field is vertical above the magnetic pole in northern Canada, and we've seen that it is pointing down at 77 degrees in Iceland, and here in the studio in Milton Keynes, it's just under 70 degrees. And this systematic variation right across the globe has been known for over 150 years. In fact, before the invention of reliable compasses, mariners sometimes used measurements of magnetic dip to work out where they were, which is what this Admiralty dip circle was used for. An instrument like this was used by Captain James Ross, for example, in his exploration of the Antarctic in the early 19th century. So how does the dip vary at the Earth's surface? Well, this model has a bar magnet inside it. Now, although the Earth's field is not produced by a bar magnet, the field has more or less the same shape as that of a magnet. Notice that at present, the magnetic axis is not aligned with the spin axis. It is about 11 degrees off. Above this end of the magnet, the field is pointing vertically downwards. As we go southwards towards the equator, the dip decreases until at the equator it is parallel with the surface of the Earth. And moving further south, the dip begins to increase again, but pointing outwards this time, until at the southern pole it is pointing vertically down out of the Earth. Let's look at the field in a bit more detail. What does the field actually look like away from the surface? If we had lots and lots of tiny compass needles, we could see this better. You've probably seen a pattern like this before. There's a bar magnet beneath, and these iron filings become magnetized in the field of the magnet and align themselves like tiny compass needles, revealing the field shape. This is a bar magnet with two poles, a dipole. So this is a two-dimensional picture of a dipole field. If we look near the poles, we can see that the iron filings are pointing upwards, suggesting that the field extends upwards above the surface. It's three-dimensional. And that's just what this shows. These telltale compasses reveal the shape of the field above the surface. From the poles, where it's steep, the inclination decreases gradually as we go away from the table, until at the top the field is horizontal, parallel to the bar magnet, and the dip increases again, pointing in the other direction, down to the other pole of the magnet, where again it's steep. So the field is three-dimensional and has this kind of shape. If we superimpose this dipolar field on the Earth, this is what we get. The curved lines are the field lines, showing how a free compass needle would line up in the field.
Now, the reason why I've come to Iceland is because the rocks here have some rather unusual magnetic properties. Let's see if I can show you the effect. If I bring the compass needle up, let's see if we can see a deflection. Ah, there we can see a deflection. So these rocks are actually magnetic. They deflect a compass needle. What we're looking at here is a large basalt lava flow. It's a lava flow that cooled and crystallized after being erupted from a volcano about 4 million years ago. And when it crystallized, the magnetism of the time was locked in. Again, roughly 77 degrees to the vertical. That's the inclination. So we can use rocks like these to actually study the Earth's magnetic field's strength and direction in the past. Leo Christiansen of the University of Iceland is using a cylindrical drill to extract a core sample for analysis in the laboratory. Leo has been studying magnetization in lava flows here for over 20 years and has extracted thousands of core samples, but before extraction, each must be precisely located.
We orientate the core accurately with respect to horizontal and vertical planes because the coring direction is generally arbitrary. And when we have measured the horizontal direction with respect to geographic objects and the vertical direction with respect to spirit level, then we extract the core and mark its upper surface permanently. Well, the samples which we collect in the field have to be cut into little specimens of the right size to fit our magnetometer probes. So I put the specimens into this holder and I measure each specimen in various orientations to obtain the three components X, Y, and Z of the magnetization. Then that information is printed out on a little printer, and we then put that into a larger computer which corrects magnetization direction for the direction of drilling, and then the final results get plotted out as a position of the geomagnetic pole on a map of the globe.
Now, if we are given a piece of rock and not told where it has been collected, can we work that out for ourselves? Well, we can. For example, if we know the orientation of this piece of rock, we could work out the magnetic dip, and hence the latitude, in the same way as Leo did. And this rock gave a magnetic latitude of about 70 degrees. Now, I have here a strip which is marked in 10-degree intervals of latitude, and I fix it to the North Magnetic Pole. So if we look on the globe for a place with this dip of 70 degrees, we know at least the magnetic latitude of the place where the sample came from. It's around this circle. But we cannot tell whereabouts on that circle it comes from, about longitude, relative position in this kind of direction. In fact, it comes from Mount St. Helens on the western coast of the United States of America, which erupted in 1980. Now, conversely, knowing the precise location where the sample came from, we can reverse the argument and find the position of the magnetic pole. Because if we know the location and the magnetic dip, we can find the latitude, and from that, the pole is the corresponding distance away to the north. If we collect rocks which span the last few thousand years, the picture seems a bit more complicated. A scatter is caused not by experimental errors, but by the variation in the angle between the Earth's spin axis and the magnetic axis. Averaged over 7,000 years, the two axes coincide. So by finding the centre of the cluster, we can get the mean position of the magnetic pole. But what happens if we go further back in time? After all, to geologists, 7,000 years ago is classified as recent. Well, if we take pole positions for Britain at 100 million year intervals back to 500 million years, we get pole positions like this. And by joining up these points, we get a line which is known as an apparent polar wander curve. Now, if the pole position for old rocks does not match today's position, then either the pole has moved or the rocks have moved. how can we be sure that it is the continents and not the poles which have been affected? The decisive evidence comes from a comparison of the apparent polar wandering curves from two continents. Let's have a look at the data for Europe, which is more or less the same as for Britain, and compare it with North America. The North America curve from 400 to at least 200 million years ago looks to be very similar shape to that from Europe for the same period, showing several kinks and trends in common, here and here, for example. Paleomagnetists quickly realized that the similarities implied that the two continents might have moved in unison from 400 to 200 million years ago. We can bring the continents together so that the curves coincide. It turns out that underwater, the continental edges fit at a depth of 1,000 meters. So the similar shapes of the apparent polar wanderpaths can be explained if the two continents came together about 400 million years ago, moved in unison until sometime after 200 million years, before drifting apart again. During all this, both continents were drifting gradually northwards, with the distance from the North Pole, the latitude, gradually decreasing. You can see now why these curves are called apparent polar wander curves. The poles have not moved at all. It is simply the continents that have moved. So by studying the magnetic dip in rocks of known age, we know the continents have moved. But at the same time, the rocks have revealed something even more surprising about the Earth's magnetic field.
Well, here Leo Christiansen is using a small magnetic sensor to sense the magnetism in its direction in the rock. Now, Leo, what about this rock? Where does it come from and what have you found?
This rock comes from the lava immediately below the one we are standing at, and this is the top end, and as I bring it up to the sensor, the deflection is towards me giving polarity which is normal magnetization.
So the magnetism in the lava that we're kneeling on here is actually normal, very much as you would expect in the Earth's present field. But behind me here is a red horizon between this material and a lava flow above. This red horizon actually represents a weathering of the upper surface of the lower lava. Usually such horizons represent a time gap of about 10 or 20,000 years. And we might see something a little bit different in the magnetism of the lava above. Let's have a look. Leo, here's a sample of the upper lava. That's the top, so see what the magnetism does.
I move it up to the sensor and it gives a deflection towards you, meaning it's reversely magnetized.
So the magnetism in the lower lava is normal, whereas that in the upper lava is actually reversed. There's been a reversal, a wholesale reversal of the Earth's magnetic field direction between the formation of these two lavas. Now, if we look over behind me, you can see a number of lava flows up the hillside. In fact, they go on to provide a very large vertical section of lavas that were erupted over a long period of time. And if we study those, we can see that the Earth's magnetism has reversed itself many times in the history of Iceland. Reversals of magnetic polarity have also been found on the ocean floor. Just south of Iceland, the strength of the Earth's magnetic field is found to be alternately higher and lower than the average for the region as a result of the magnetism frozen into the rocks of the ocean floor. By subtracting the Earth's field, we are left with anomalies which amount to about 2% of the total. The completed survey shows regions of positive and negative magnetic anomaly where the Earth's field is alternately reinforced and partly cancelled by rock magnetism. These regions form linear strip-like patterns parallel to the axis of a submarine ridge which is volcanically active. The real pattern's a bit more complicated because of uneven rates of volcanic eruption. Now, we know the timescale of reversals from the vertical piles of dated lavas such as those in Iceland, and this scale can be matched with the anomaly pattern on either side of the ridge. This gives us a method of dating the ocean floor. Now, this has been done, and the dates fit with the idea that the rocks of the ocean floor form and spread laterally away to either side of the ridge. This is known as seafloor spreading. Furthermore, we can measure the distance between a particular anomaly and the ocean ridge, this distance, Simply by dividing by the time elapsed, we can find the rate at which ocean floor material is being produced either side of an ocean ridge, typically a few centimetres a year. Now, during seafloor spreading, partially molten material is brought up continually from the mantle. It becomes magnetized in the direction of the Earth's field as it cools. If the polarity of the Earth's field changes, the magnetization will change. During periods of reverse magnetization, a negative anomaly is formed, and so the process continues, producing strips of alternating polarity and hence alternating positive and negative anomalies. These strips are parallel to the ridge, and if the material spreads evenly on either side, the anomalies on one side of the ridge are the mirror image of those on the other side.
So the study of rock magnetism has produced very convincing evidence for the movement of continents. But you may well be wondering how the Earth could have a magnetic field which looks just like that of a bar magnet, and yet which can reverse in just a few thousand years, quite quick in geological terms. Well, remember that at the moment in Britain, the dip of the field is about 70 degrees downwards, like this. Oh, hello, it's changed. It seems to have reversed. There must have been some kind of reversal. How is that possible with a bar magnet? Well, we're fooling you, really. This is a different globe with a coil carrying an electric current. And the needle flipped over because Jeff turned this switch to reverse the current. Now watch that again. Now, I'm not suggesting there's a coil like this inside the Earth any more than there's a bar magnet. But this does show that the Earth's magnetic field could be produced dynamically. Electrical currents circulating within the core could produce the field, and this gives us a simple way of explaining field reversals. Now, notice that just as with the bar magnet, the field at the end of the coil is steeply downwards, and as we move the needle round towards the equator, the dip becomes less, until at the equator it's horizontal, parallel with the Earth's surface, and then going southwards towards the other end of the coil, the dip increases until right at the bottom it's pointing vertically outwards. So the dip seems to vary in the same way as the bar magnet. Is the shape of the field the same in detail? As before, we can use iron filings to reveal it. This is a coil, and the iron filings move in the same kind of pattern from this end of the coil round in a loop and back into the other end of the coil, just like it did on the bar magnet pattern. And if we use the telltale compasses and put them above the coil, you can see in exactly the same way that they form an arch pattern above the coil. And an extra thing we can show here, if we just reverse the current like this, the needles all flip over and are pointing in the opposite direction. So an electric current flowing through a coil can produce a dipole field like that of the Earth.
But is the Earth's field exactly that produced by a dipole? Well, here's a map showing theoretical contours of field strength for an Earth with a simple inclined dipole, where the positions of the magnetic poles in the northern and southern hemispheres are specified. But this is what the field actually looks like. To a first approximation, the values of field strength are similar to those of the theoretical dipole model, decreasing from poles to equator, but the contours are far less regular, and the field intensity maxima do not coincide with the positions of the poles of the best fit dipole field, Mn and Ms. Moreover, the dip poles, Pn and Ps, where the inclination actually is 90 degrees, are some distance from Mn and Ms, and from the zones of maximum observed field strength. What this means is that the Earth's field is not quite that of a dipole, and there is a significant non-dipole component which you can think of as being superimposed on the dipole field. In fact, this component varies in strength and direction quite quickly. By subtracting the best fitting theoretical dipole field from the observed field, we can isolate the non-dipole component. Using historical data, Roy Thompson of Edinburgh University has reproduced the changes in the non-dipole component for the last 400 years. If you watch carefully, you'll see the highs and lows growing, shrinking, and moving with time. Generally, they're moving westwards from right to left. These rapid changes in the Earth's magnetism strongly imply a dynamic origin for the field. So we need a dynamic mechanism for producing the field from electrical currents within the Earth. Now, this problem has exercised scientists for quite a long time. This Victorian device was built to model the changes in the direction of the Earth's field at the surface. Inside the globe is a second sphere with coils which carry an electric current to produce a magnetic field. Now, notice that the magnetic axis is inclined, reflecting the angle between the Earth's magnetic and spin axes. But this model shows more than just a dipole field. These thin steel plates are magnetized and were inserted to produce local field variations which match the observed non-dipole field component. Now, taken together, when the spheres are rotated, with current passing through the interior coils, the field strength and direction can be modeled using this dip circle. And by adjusting the relative positions of the different spheres and the plates, the field can be modeled for different times. Now, at the time this globe was made, the fact that the field had reversed many times in the past was not known. Furthermore, the field is simulated by shallow coils at mantle depths, whereas the source of the Earth's magnetism lies in the central core, some 3,000 kilometers deep.
Now, 100 years later, we're still trying to model the Earth's field. Nowadays, however, the aim is not to reproduce the field, but to model a generation mechanism. For example, this model has been made by Ian Wilkinson and colleagues at the University of Newcastle. Of course, it looks nothing like the core, but it is made of iron like the core. And within here, 2 iron cylinders can be rotated by motorized pulleys. So in effect, we have a continuous piece of iron with 2 rotating parts. Now, this is a probe with which we can detect a magnetic field, and it's connected to a meter, which at present is showing 0 in the center of the scale. Now, if I bring this bar magnet close, you can see the meter shows a deflection, and if I take it away, it goes back to 0. So let's rotate one cylinder first and see what happens. Well, nothing at all. So now we'll try it with both cylinders rotating. Well, that certainly produced a field, and so it must be the result of an interaction between the 2 rotating cylinders. Now, if I run it again, and whilst it's running, turn one motor off, then the field dies away. So this is a self-exciting dynamo. There are no electrical connections to the iron block, so the field must be generated entirely within by the interaction of self-excited currents and magnetic fields. Now, we can build models like this with more rotors, and they produce a field on the same principle. And furthermore, on these models, the field undergoes spontaneous reversals. Although we still don't understand how this works, at the very least, this self-exciting dynamo model reproduces 2 key aspects of the Earth's field: its dynamic origin and spontaneous field reversals.
Now, in this program, we've shown you a range of models which have been devised to explain the origin of the magnetic field. Even with the sophistication of modern techniques, we can still only produce models which will never be tested by direct observation of the outer core some 3,000 kilometers beneath us. But we feel sure that the field is produced by some form of dynamo action. With an origin in the deep interior, and although invisible at the surface, the Earth's magnetic field is nevertheless responsible for some of the most spectacular displays of nature.
Plant to turn towards the